There are four little symbols that show up in the margin of almost every physics textbook, right around the chapter you skip. A curl here, a dot there, an E and a B, leaning on each other like they're holding each other up. I used to flip past that page every single time. Not because I decided it was boring, because somewhere, without ever noticing, I decided it wasn't written for me. I've watched documentaries where the camera lingers on those same four symbols chalked on a blackboard. The narrator says something reverent about the elegance of physics and moves on before anyone has to actually read them. I nodded along like I understood the reverence, then quietly filed the whole thing under things I will never need to know. Here's what finally stopped me from flipping past it. Those four symbols aren't a wall. They're a diary. Four short entries, written by nature itself. And once somebody hands you the translation, you realize the diary was never locked. Nobody ever gave you the key. That's the only reason it looked hard. By the end of this video, you're going to read all four entries yourself. In plain English, no symbols required. You're going to watch two things that seem to have nothing to do with each other turn out to be the exact same thing, wearing two different costumes. And you're going to find out that the light hitting your eyes right now is the punchline of a joke nature has been quietly setting up since 1831. Let's open the diary. Start with something you could do on your own kitchen table. Take a bar magnet. Lay a sheet of paper over it. Sprinkle iron filings across the top. Tap the paper once. The filings don't scatter randomly. They snap into curved lines, looping out from one end of the magnet and back into the other, like the magnet is combing the space around it into shape. A shy, self-taught experimentalist named Michael Faraday did exactly that in the early 1800s, and he took the pattern more seriously than anyone else had. Most of his contemporaries looked at those curved lines and saw a diagram. A convenient way to sketch a force, nothing more. Faraday looked at the same lines and saw something closer to a claim. He decided they weren't just a way of drawing the magnet's pull. He decided they were there, physically, filling the space around the magnet whether you sprinkled filings or not. He called this a field, and he insisted it was as real as the magnet itself. This did not go over well in the rooms where the actual mathematicians worked. Faraday had almost no formal schooling. He'd spent his teenage years bound as an apprentice to a bookseller, and the story goes he taught himself science from the very books he was supposed to be binding shut instead of reading. He talked his way into a laboratory job scrubbing bottles, and from nothing but stubborn curiosity became, quite possibly, the greatest experimentalist of his century. What he never picked up along the way was calculus. He couldn't write down an equation to save his life. So when he stood in front of trained physicists and told them empty space itself was filled with invisible lines of force, he had no mathematical proof to offer, just the filings, and his own certainty. The mathematicians of the day were not shy about how they felt about this. To them, a field was, at best, a convenient bookkeeping trick, a way of sketching how one charged object might eventually push on another one far away. Real physics dealt in forces acting directly between particles, not poetic talk of invisible lines filling up empty space like some kind of atmosphere. Faraday had no formal way to answer them back, so he didn't. He just kept running the experiment, again and again, with different magnets and different arrangements, and the filings kept snapping into the same looping shapes every single time. He trusted the pattern more than he trusted his own inability to defend it in the language everyone else insisted on using. That was entry 1 in the diary. A magnet fills the space around it with something. Entry 2 came from a completely different direction, almost by accident, in a Copenhagen lecture hall in 1820. A professor named Hans Christian Ørsted was demonstrating something entirely unrelated when he noticed a compass sitting near a wire go haywire the instant he switched on a current. No magnet anywhere close, just moving electric charge and a compass needle swinging like there was one. Electricity, somehow, was producing the exact same invisible push that Faraday's magnets produced. Two phenomena that had lived in separate scientific neighborhoods for a century. Electricity over here with its sparks and batteries, magnetism over there with its lodestones and compasses, had just been caught touching. Ørsted never fully chased down what he'd found. He published the observation, noted that the effect seemed to circle the wire rather than push straight toward or away from it, which was strange enough on its own, and largely left the deeper implications for someone else. It was enough, though, to end a century of assuming electricity and magnetism were permanently unrelated. The wall between the two had a crack in it now. There was no putting it back. Faraday spent the next decade chasing the reverse question. If electricity can produce a magnetic push, can a magnetic push produce electricity? In 1831, he wired up a coil, held a magnet perfectly still beside it, and got nothing. Silence on the meter. But the moment he moved the magnet, current flowed. Stopped the motion, the current stopped. It wasn't the magnet's presence that mattered. It was the change. A shifting magnetic field, and only a shifting one, could push electricity through a wire. Every generator on the planet, every turbine spinning a magnet past a coil of copper right now, somewhere, is this one entry from the diary, running on repeat, at industrial scale. Sit with how strange that distinction actually is, because it's easy to skim past. Hold the magnet perfectly still an inch from the coil, and you could leave it there for a year without drawing a single electron out of the wire. Move it, even slightly, and current appears immediately, then vanishes the instant the motion stops. The coil isn't responding to the magnet being nearby. It's responding to the magnet's presence changing, moment to moment. Faraday had no equation to explain why the universe cared about change specifically, rather than mere presence. He just had the meter, refusing to move until something moved first. 2 entries down. Electricity in motion produces a magnetic field, and a changing magnetic field produces electricity. Faraday had both of them in hand, and no way to write either one down properly. What he needed wasn't another experiment. He needed a translator. Somebody fluent in the language he couldn't speak. That translator turned up in the form of James Clerk Maxwell, a Scottish physicist with the opposite skill set entirely. Middling at building apparatus. Ferociously gifted with mathematics. Where most of his peers dismissed Faraday's invisible lines as a charming but unrigorous mental crutch, Maxwell did something almost nobody else was willing to do. He took the picture at face value. He decided the field was real, exactly the way the untrained bookbinder's apprentice had insisted it was, and set out to write it in equations. Maxwell had actually met Faraday, by then an old man near the end of his career, and the two of them corresponded for years afterward. Faraday, by his own admission, could barely follow the mathematics Maxwell was sending him, and Maxwell, for his part, spent enormous effort making sure his equations never drifted away from what Faraday's hands had actually found on the lab bench. It's an unusual partnership in the history of science. One man supplying the physical intuition he couldn't formalize. The other supplying the formalism he was careful never to let outrun the intuition. What Maxwell produced was a set of 4 statements, each one a translated diary entry, together covering everything anyone knew about electricity and magnetism. Let's read all 4. Plain English. No symbols. Entry 1. Any electric charge fills the space around it with an electric field, spreading outward like ripples from a stone, pointing away from a positive charge and inward toward a negative one. Charges are where the field is born. Entry 2. The magnetic version of that same idea, except with a twist. Magnetic field lines never start or stop anywhere. They only ever curl back on themselves in closed loops. Translated into a physical fact, that means you can never isolate a single magnetic pole. Snap a magnet in half hoping for a lone north and a lone south, and each fragment instantly grows its own complete pair. Take a bar magnet, saw it neatly down the middle, and you don't end up with an isolated north in one hand and an isolated south in the other, the way you'd reasonably expect. Each half instantly becomes a complete, smaller magnet, north and south both, as though the missing pole regrew the instant the metal was separated. Cut those halves in half again, and the same thing happens. Indefinitely, down to the smallest scale anyone has ever managed to test. Physicists have spent entire careers hunting for a genuinely isolated magnetic pole, a monopole, in cosmic ray detectors and particle accelerators alike. Nobody has ever caught one. Entry 2 isn't a suggestion. It's held up under every test anyone has ever thrown at it. Entry 3 is Faraday's moving magnet result, formalized. A changing magnetic field creates an electric field. Entry 4 is Ørsted's twitching compass, formalized. An electric current creates a magnetic field circling around it. For sentences, 2 about electricity, 2 about magnetism, and a pair of bridges running between them. Read them back to back, and there's nothing here that requires a physics degree to follow. Charges are where field lines start. Magnetic lines never start, only loop. A changing magnet makes electricity. A current makes a magnet. That's the whole diary. Translated, the intimidating part was never the content. It was 4 unfamiliar squiggles standing in front of 4 perfectly ordinary sentences. And it's those 2 bridge entries, 3 and 4, where the real story is hiding. Maxwell didn't just transcribe the 4 entries and call it finished. He did something better. He audited them, the way you double-check a ledger before signing off on it. Entry 4, the one about currents producing magnetic fields, didn't balance. Here's the discrepancy, and you only need one piece of equipment to see it: a capacitor. Nothing more than 2 metal plates facing each other with a small gap of empty space between them. Wire it to a battery, and charge starts piling onto the plates. While that's happening, current is flowing through the wire feeding each plate, and a current flowing through a wire produces a magnetic field around it. Fine so far. Entry 4 is satisfied right up to the edge of each plate. But look at the gap between the plates. Current flows into one plate and out of the other, but nothing actually crosses that gap. It's empty space, with nothing in it but a growing electric field as charge accumulates. So by Entry 4's own logic, there's a magnetic field circling the wire right up until the gap, and then, according to the rule as written, no current means no magnetic field in the gap itself. The magnetic field should vanish in the middle and somehow reappear on the far side. That's not a subtle inconsistency. That's a ledger that doesn't close. Put a number on it, and the discrepancy gets even harder to wave away. Charge a small capacitor with an ordinary current of, say, 1 amp. Entry 4 says that current should be wrapping the wire in a magnetic field of a specific, calculable strength, and instruments confirm it does, right up to the plate. Walk your measuring probe into the gap itself, where by definition no charge is crossing, and the old version of Entry 4 insists the field there should read exactly 0. Instruments disagree. There's a magnetic field in the gap too, roughly matching the one just outside it. As if the circuit didn't know it had a gap at all. The rule on the books and the reading on the meter were describing 2 different universes. Nobody else seemed bothered enough to lose sleep over it. Maxwell did. With no new experiment and no fresh data. Purely on the conviction that a correct description of nature shouldn't contradict itself, he proposed a fix. What if it isn't only a moving current that produces a magnetic field? What if a changing electric field does the identical job, entirely on its own, with no charges moving through it at all? In the gap of the capacitor, the electric field is growing every instant as charge piles onto the plates. Maxwell said that growth itself counts, functioning exactly like a current for the purpose of generating a magnetic field. He called it the displacement current, and he wrote it into Entry 4 with essentially nothing to justify it except the demand that the books balance. Now line the 2 bridge entries up, side by side, and something extraordinary falls out. Entry 3 says a changing magnetic field produces an electric field. Maxwell's patched Entry 4 says a changing electric field produces a magnetic field. Read them again. Each one is the trigger for the other. Picture it as an echo instead of a leapfrog. Give an electric charge one small shake. That shake is a changing electric field, and a changing electric field, per Maxwell's repaired 4th entry, immediately calls a magnetic field into being right beside it. But that new magnetic field had to grow from nothing, which means it's changing too. And a changing magnetic field, per Entry 3, calls a fresh electric field into being a little further out. That field is also changing, so it calls another magnetic field further out still. Electric, magnetic, each one the echo of the one before it, each echo strong enough to trigger the next, sprinting outward through space that started out completely empty. That is a wave. It needs no medium, no substance to vibrate through. Because the two fields are entirely capable of sustaining each other, an echo that never needs a canyon wall to bounce off of, because it's producing its own next reflection as it goes. This is the single idea worth carrying out of the whole video, so let it sit for a second. Every wave you've met before this one needed a medium. Water for an ocean wave, air for a sound wave, a string for a guitar note. This is the first wave you've ever encountered that builds its own medium out of nothing, one echo at a time, faster than you could ever hope to watch it happen. Maxwell, being the type who never leaves a good result alone, immediately asked the obvious next question. How fast does this echo travel? The mathematics answered with unsettling precision. The speed came out to 1, divided by the square root of 2 specific numbers. And here's the detail that should raise the hair on your arms. Neither of those 2 numbers had anything to do with light. One is measured by seeing how hard 2 charged objects push each other apart. The other is measured with a coil of wire and a magnet. Both numbers were already sitting in physics textbooks, gathered on lab benches with nothing but batteries and copper, decades before anyone thought to connect them to anything optical. Maxwell multiplied them together the way the mathematics demanded, took the square root, and out came a number close to 300,000 kilometers per second. He recognized it instantly. Everybody did. It was the measured speed of light, clocked by astronomers and mechanical engineers using entirely separate methods, for an entirely separate reason. Take a moment to appreciate how little of this was aimed at light on purpose. One number came from measuring how hard 2 pith balls repel each other on a string. The other came from measuring how strongly a coil deflects a compass needle. Neither experiment involved a candle, a lens, or a beam of sunlight anywhere in the room. And yet run them through Maxwell's audited equations, and a speed falls out that matches, digit for digit within the precision of the era, the number astronomers had spent 200 years chasing with telescopes pointed at eclipsing moons and spinning mechanical mirrors. There's exactly one honest conclusion available when a coincidence lands that clean. Light itself is this echo. Electricity and magnetism, chasing each other outward through empty space, is what light physically is. Maxwell wasn't hunting for an explanation of light when he started. He was auditing a capacitor. He stumbled into the answer to one of the oldest questions in physics on his way to fixing an accounting error. There was, however, a problem nobody could quite let go of. Every other wave anyone had ever encountered needed something to wave through. Sound needs air. Ocean waves need water. So if light is a wave, the thinking went, it must be rippling through some substance that fills all of space. Scientists gave that hypothetical substance a name, the luminiferous ether. They were confident it existed because a wave with nothing to wave in felt like a contradiction in terms. Except Maxwell's own equations never asked for one. The electric and magnetic fields hold each other up entirely on their own. For the rest of the 19th century, physicists built increasingly precise instruments specifically to detect this ether. And the harder they searched, the more thoroughly it refused to be found. The most famous of these hunts, run by Albert Michelson and Edward Morley in 1887, was built with the express purpose of catching the ether in the act. Their apparatus split a single beam of light into 2 perpendicular paths, bounced each half off a mirror, and recombined them, reasoning that Earth's own motion through the supposed ether should very slightly speed up light traveling one direction and slow down light traveling the other. Any such difference would show up as a shifting interference pattern, light and dark bands drifting as the whole device was rotated. They built it sensitive enough to catch a difference far smaller than anyone expected to need. It caught nothing whatsoever. Rotate the device any way they liked. The bands refused to shift. That null result, that stubbornly missing ghost, would end up being one of the most important clues in the entire history of physics. Maxwell himself never lived to see any of this vindicated. He died in 1879, at just 48, years before his predicted invisible waves were ever produced and detected in a lab. It fell to a young German physicist named Heinrich Hertz, working nearly a decade after Maxwell's death, to build the apparatus that finally caught one. A spark on one side of a room. a matching spark jumping across a small loop of wire on the far side, with no wire connecting them at all. Hertz had generated and captured an invisible echo out of nothing but Maxwell's math. He spent the following months mapping the new phenomenon obsessively, how it reflected off metal sheets, how it could be focused with a curved surface, the way a lens focuses light, how it passed through some materials and not others, confirming, point by point, that it behaved exactly the way a very long wavelength cousin of visible light should. When someone asked him what practical use his discovery might have, he reportedly shrugged and said none. That useless spark is the direct ancestor of every radio broadcast, every Wi-Fi signal, and every phone call happening on the planet at this exact moment. Once you know light is this electromagnetic echo, a new question opens up immediately, because an echo can come in any size. The narrow band your eyes can actually detect is a thin slice of a much longer range. Stretch the echo out and you get infrared, which you feel as warmth, then microwaves, then radio waves that can be meters long. Compress it instead and you get ultraviolet, then X-rays, then gamma rays energetic enough to come screaming out of a collapsing star. All of it, every single entry in that range, is the identical mechanism. A changing electric field calling a magnetic field into existence, calling another electric field, over and over, just tuned to a different size each time. The narrow rainbow you can see with your own eyes is one small stretch on an instrument that extends for miles in both directions. Every antenna ever built, from the one folded up inside your phone to the dish pointed at a satellite, is a piece of metal engineered to do one specific job: shake electrons back and forth at a precise, controlled rate so that entries 3 and 4 keep triggering each other outward in a clean, predictable size. Broadcast at the wrong rate, and the echo comes out the wrong size for the receiver listening for it. Get the rate right, and you've built a machine whose entire purpose is manufacturing one particular translated diary entry on demand, billions of times a second, and firing it into the sky. Look around any ordinary room and you're surrounded by different sizes of the identical echo, doing different jobs purely because of how far apart its peaks happen to be. The microwave oven on the counter is tuned to a size that happens to jostle water molecules efficiently, which is the entire secret behind reheating leftovers. The Wi-Fi router blinking in the corner is broadcasting a slightly different size, chosen because it slips through drywall without much trouble. A dentist's X-ray machine is running the same mechanism compressed down to a size small enough to pass through soft tissue and stop at bone. And the gamma rays pouring out of a collapsing star, the most energetic light in the universe, are the same echo compressed further still, born from stresses no laboratory on Earth could replicate. Different size. Identical translation of the same 4 entries. There's one more thread worth pulling before we close the diary, because it leads somewhere enormous. Remember those 2 ordinary numbers Maxwell multiplied together to get the speed of the echo. They describe properties of the vacuum itself, not properties of light. Which means the number we call the speed of light isn't really a fact about light at all. It's stitched into the structure of empty space. And that carries a consequence that took the world roughly 40 more years to fully accept. If that speed is set by the structure of space itself, it has to be the same for every observer, no matter how fast they're moving. Chase a beam of light, run away from it, stand perfectly still, and you measure the identical number every time. That is not how anything else in the ordinary world behaves. Speeds are supposed to add. A patent clerk in his 20s named Albert Einstein took that fixed speed completely seriously, and worked out that the only way to keep it fixed was for something else to bend instead. Time itself turned out to be the thing that gives. Special relativity, moving clocks running slow, mass and energy turning out to be interchangeable. All of it grows directly out of taking Maxwell's speed seriously. You've already benefited from this without ever reading a line of the original diary. Every GPS satellite quietly carries a clock that engineers deliberately mistuned before launch, specifically to compensate for the fact that a clock in orbit runs at a measurably different rate than one on the ground, a correction that traces its lineage straight back to a Scottish physicist auditing a leaky capacitor. Nobody sat down in the 1860s intending to eventually correct satellite navigation. Maxwell was just making sure 4 short entries in a diary added up honestly. His 4 little translated entries didn't just explain what light is. They quietly unlocked the door to the entire next century of physics, and nobody realized it was a door until somebody else walked through it. So here's the diary, closed and read in full. A magnet fills space with a real, physical field. A changing magnetic field produces electricity. An electric current produces a magnetic field, and, thanks to one stubborn audit of a capacitor, so does a changing electric field, with nothing else required. Line the last 2 entries up and they trigger each other endlessly, sprinting outward through empty space as a self-sustaining echo. That echo is light, at every size from radio waves to gamma rays, moving at a speed baked into the fabric of the vacuum itself, a speed so fixed that it eventually forced the entire concept of time to bend around it. A bookbinder's apprentice who couldn't do calculus felt the truth of it in his hands, sprinkling iron filings on a sheet of paper. A professor in Copenhagen noticed a compass needle twitch during an unrelated lecture and refused to write it off as an accident. A translator with a gift for mathematics wrote it all down properly, corrected the 1 entry that didn't balance, and stumbled into the nature of light while trying to fix his own accounting. A German physicist built a spark gap in an empty room and caught, for the first time, an echo nobody could see. And a young patent clerk, decades later, took the diary's fixed number seriously enough to rebuild time itself around it. That's not a page to flip past. That's the moment 4 short entries in nature's own diary turned out to be the reason you can see anything at all. The reason a phone in your pocket can talk to a satellite. And, eventually, the reason clocks don't tick at the same rate for everyone. None of that was hiding in the difficulty of the symbols. It was hiding behind them the entire time, waiting for someone patient enough to sit down and actually translate. If this rearranged how you look at those symbols in the margin, subscribe, because the fixed number Maxwell found is about to unravel time itself. And that's exactly where we're headed next. The diary's open.